Section 3.2 is about differentiability, which really means that the derivative exists at a point. So there are 4 different ways that a function can fail to be differentiable at a point. One way a function can fail to be differentiable is if a corner exists at the point. So if you look at this picture, it's a picture of a corner on a graph. And to the left, the slope of the tangent lines are all -1, or the slope of the function is -1. To the right, the slope of the function is +1. Both of those slopes exist. They're both number answers, but they don't match, and so that's called a corner. The second way to be differentiable, if I drew tangent lines to these 2 curves, so if I drew tangent lines of this function, the tangent to the right is approaching vertical. All of these slopes are uphill, and so the tangent line is approaching vertical, and a vertical slope means that you're trying to divide by 0. So to this side, the slopes going this way are approaching positive infinity. If I drew tangent lines in the other direction, they're all downhill lines. It's a decreasing slope, but approaching vertical. So to the left, my slopes are approaching -infinity. For a cusp, the slopes from both directions approach infinity, but they don't match the same kind of infinity. So that's called a cusp. This third graph, in this example, all of my tangent lines are downhill tangent lines, so this function is always decreasing. But at 2, my tangent line is vertical. And if I look at the function in the other direction, there's still downhill tangent lines in this direction, but they're approaching vertical as I get closer to 2 in the negative direction. So both of these 2 slopes are approaching -infinity. Or as I approach 2 from both directions, my slopes are approaching -infinity. It's the same type of infinity. That is a vertical tangent line. The fourth type is if you see a discontinuity. Anytime you see a discontinuity, your function is not differentiable, and even if it's just a hole. So a removable discontinuity still counts. If you have a hole, you can't draw a tangent line at that point. It's maybe a little bit counterintuitive, but I guess in order to write a tangent line equation, you need an x-coordinate, you need a slope, and you need a y-coordinate. And at this point here, you have an x-coordinate and you kind of have a slope, but you don't have a y-coordinate. So you can't really draw a tangent line at x equals 2. So those are the 4 types of ways not to be differentiable. It would also count as a discontinuity if you had a vertical asymptote, or any of the other types of discontinuities. So here's an example of a corner, and we can prove to ourselves that it's a corner. So first we should prove that it's continuous, because if it's not continuous, then it's not differentiable without even checking slopes. So the limit as x approaches 1 from the positive direction, I would use this part of the definition. So I would have 1 over 1, which is 1. The limit as x approaches 1 in the negative direction, I would use the other part of the definition, and I would get just 1. And so f of 1 exists, and it's equal to 1. And so since all 3 of these things match, I know that my function is continuous. Now I need to check to see if the slopes match. If the slopes are the same thing, then the derivative exists. For the top part of the definition, I don't have to use calculus at all. I know that the slope of the x graph is going to be 1 because it has a slope of 1, because it's linear. For the other part, I have to use calculus of some sort. I can use either definition for the derivative, and I'm going to choose to use the new one just so we can have some practice with that. So we're going to take the limit as x approaches a of 1 over x minus 1 over a over x minus a. And then I'm going to find a common denominator. So I have x minus a over my common denominator, which is x times a. Oh, I did that wrong. I have a minus x. I'll slow down a little bit. I have a over ax minus x over ax over x minus a. So then I have a minus x over ax times 1 over x minus a. And what I notice is that a minus x and x minus a are almost exactly the same thing, but they're not exactly the same thing, but I can make them the same by factoring out a negative 1. So if I look at this, I have the limit as x approaches a of negative 1 times x minus a over ax times x minus a, and now my x minus a's can divide to make 1. And now I can plug in my limit, so I get negative 1 over a squared. Remember that we're evaluating this at 1, so if I do f prime of 1, I get negative 1 over 1 squared, so I get negative 1. That slope does not match the other slope, but both are numbers, so I know it's a corner because both of my slopes are numeric, but they don't have the same value. Okay. Cusps and vertical tangents, for now we're just going to try to recognize those on our graphing calculators. Eventually I'm going to teach you how to differentiate these with a shortcut, and when you differentiate them with a shortcut, you can see the cusp. But I'm going to give you the derivative, so I'm not going to go through the work of doing it, but I'm going to give you this derivative. So f prime of x is 2/3 times x to the negative 1/3. And so if I look at that as a fraction, I have 2 over 3 times the cube root of x. So one thing that you can see, and I'm just telling you this derivative, you don't have to know where that came from, but what I notice is that x certainly can't be 0. I know there's a discontinuity on the derivative at x equals 0, a vertical tangent line at x equals 0 for the derivative function. Not for the original function, but for the derivative function, there's a vertical tangent line at x equals 0. Or, a vertical asymptote. I said that wrong. Let me back up. I know that the derivative function has a vertical asymptote at x equals 0 because it's 2 divided by 0. That's a sign of a vertical asymptote. Okay? So, since I know the derivative doesn't exist at x equals 0, I know that it is not differentiable at x equals 0, and then I can look at the limit. I can look at the two kinds of infinity. So limit as x approaches 0 from the positive direction of 2 over 3 times the cube root of x. Well, if x is positive and I take the cube root of it, I'm going to get a positive number, so that's going to be positive infinity. And if I take the limit as x approaches 0 from the negative direction of 2 over 3 times the cube root of x, if I plug in a negative number, the cube root of a negative number would be negative, so this would be a negative infinity. Two types of infinity, they don't match. For now, you're going to recognize that shape on a graph, but I want you to know that it is totally possible to prove that you have a cusp using calculus. Right now, we just don't know how to find this derivative. Same thing is true for a vertical tangent. Right now, the best you're going to do is you're going to be able to recognize it on your graphing calculator, but eventually, when you know how to find this derivative, you'll say, oh, the derivative of that is 1/5 x plus 1 to the negative 4/5. So it's going to be 1 over 5 times the 5th root of x plus 1 to the 4th power. And I recognize that x equals negative 1 is going to cause me this function not to exist. So I have a problem at x equals negative 1. And if I take the limit as x approaches negative 1 from the negative direction, of f prime. I'm looking at the derivative now. So if I plug in something a little bit smaller than -1, well, I would take it to the 4th power, which would make it positive, and then I would take the 5th root of that, so I would get a positive infinity. And similarly, if I take the limit as x approaches -1 from the positive direction of f prime, I would have a positive, because -1 and +1 raised to the 4th power would be positive no matter what, and then the 5th root of that would be positive. So this is going to be a positive infinity. These two infinities match, which is how I can recognize that I have a vertical tangent at x equals -1. Turns out the sketch looks something like this, I believe. You have to take a look at it on a grapher. The other reason you could have a failure for a derivative to exist is if you have a discontinuity. So if I look at this function can be factored as x plus 2 times x minus 2, and as x minus 2 times x minus 5. So I know that there are places that are non-differentiable at x equals 2 and x equals 5. X equals 2 is just a whole, but that still counts as discontinuity, and x equals 5 is a vertical asymptote. So I know that asymptote. So I know that the function is not differentiable at that point as well. So that's a bit about differentiability and the ways you can fail to be differentiable. We'll get more into this next section as we start learning how to actually take derivatives of functions using the shortcuts.